All right, so today we are on 1.4, which is on polynomial functions and rates of change. Okay, so just to go over again, so what we should be able to do by the end of this is to identify key features of polynomial functions and how they are related to the rate of change. So the first thing is let's fill out some of this vocab. So we have a polynomial function is any function represented equivalent to the analytical form. And there you are. So again, I know that that's a lot of like math lingo, but basically what is really important to take away from this is that a polynomial is a function that has multiple terms. Okay, so remember a term, like this is a term, that's a term. Okay, so polynomial function that has multiple terms where the highest exponent is a positive integer, okay, and then all of the numbers before the variables must be real numbers, okay. So the next thing, let's look at this. So we call the first term the leading term, okay, so the leading term is going to be your first term. So if we look at this, that was our first term. Again, don't worry too much about the math lingo, just as long as you can understand where they are. The degree of the polynomial is n. So remember, that's going to be our greatest exponent. Okay, that is the degree. Okay, and then the final one, so the leading coefficient. Remember, coefficient is a number, no variable. Okay, so for example, say our polynomial is, 3x to the fourth. Again, I'm just making up a random one. The leading term would be this entire thing, but the leading coefficient would just be the number 3. Okay, and in this example, the degree would be 4 because that's the greatest exponent. All right, so let's try a few practice problems, see how we do. All right, so we're looking for the leading coefficient, again, not leading term, leading coefficient, and the degree of each of these polynomials. All right, so let's look here. So letter A, so we have f of x equals 3x to the fourth plus 2x minus 7. So the leading coefficient is that first number, okay, so that would be 3. Okay, and then the degree, remember, is the greatest exponent, which in this case would be 4. Okay, if you want to pause to try the next two, feel free. All right, so the next one, leading coefficient, again, number there, not the whole term, so that would be 7. And then degree, again, highest exponent, so that's going to be 3. All right, and the last one, again, leading coefficient, not whole term, so in this case is 4. And then the degree, well, you might say, wait a minute, there is no exponent. But don't forget that if we have a variable without an exponent, it is implied to be 1, right? So remember that if you have a variable with no written exponent, it is implied to be an exponent of 1, making our degree 1. Okay? Now, we do have to be careful in noticing that sometimes the polynomials are not written in standard form. Again, remember, standard form is when it's written greatest exponent to least. Okay, so all the ones that we had in number 1, A, B, and C, they're all in standard form. Okay, highest or greatest exponent, to the least. Now, if we have one that's not written in standard form, okay, we have to make sure that we're looking at the variable's largest exponent to find the leading term and to determine the degree. Okay, so let's look at A here. So we notice that 8x is the first term, but that's not the term with the greatest exponent. So 6x cubed, okay, has the greatest exponent. So that's what we're going to look at to determine leading coefficient and degree. So the leading coefficient here is that number, so that would be 6. And then that degree would be its exponent, so that would be 3. Again, let's look at another example. So again, we notice we have 14x squared, 6x, negative 2x to the 6th plus 1. So the 6th is the highest exponent there. Okay, so that is the term that we're going to use. The leading term, some of you might think it's just 2, but don't forget that sign is going to go with it. Okay, so it would be negative 2. Okay, and that degree again goes based on the exponent, which is 6. Alrighty, let's continue on. All right, now we're going to talk about what we call extrema. Okay, so extrema are where on the graphs your functions are going to hit minimums and maximums. And while we're working through this, it's helpful to know that there are 2 different types of extrema. Okay, the first type that we have, we call them relative or local. So it's important to be able to identify that both the term relative and local are used interchangeably. Okay, so a relative minimum or relative maximum occurs when the function switches between decreasing and increasing. Now, make sure you understand that that means it could be going decreasing to increasing or increasing to decreasing. It's just when you notice a switch. Additionally, it could also be at an endpoint if the domain is restricted. And what I mean by that is if, say, you're given a function and it's got definitive endpoints, okay? So like in my example here, if you notice these, that is a solid dot, whereas that is an arrow. Okay, so this would be considered an endpoint because we're saying that my function is not continuing on the left side. However, because this is an arrow, it is continuing on, okay, forever and ever as x gets closer to infinity. Okay, so that's the first type. So let's look at that here. Okay, so the question says local minimums. So again, minimums are where they're changing from increasing to decreasing or decreasing to increasing. Okay, that's where we find the relative. Now we have to decide which one's minimum and maximum. So if we notice here, okay, this is increasing, and then we go decreasing, and then we go increasing, and then we go decreasing. So anywhere along that line where those 2 things are changing, okay, so where the colors change, that would be either a local minimum or a local maximum. Now we just have to decide which one's min and which one's max. Okay, so let's look at minimums. So minimums would be those low points, right? So if I look, let's just go left to right. Here, this endpoint right here, where x equals negative 4, is a low point. Okay, let's keep going. All right, if we look here, where x equals 0, again, that's where it's shifting from decreasing to increasing. And because it is minimum at the bottom of that, okay, that would also be a minimum. So we have a minimum at x equals negative 4 and a minimum at x equals 0. Now, conversely, let's look for maximums. So maximums are going to be those high points. So if we look right here, we see the graph was increasing and then it's decreasing. So that means I have a maximum at negative 2. And if I continue on my graph here, and I notice right here, it was increasing and then it went to decreasing. So I also have a local maximum at x equals 3. Okay? Now let's look at the other type of extrema. So they're called absolute or global. Again, it's important to realize that this terminology is interchangeable. Okay, so absolute or global All right, they are interchangeable. So now what we have to do is realize, so for all the local minimums or all the local maximums, so the local maximums, the greatest one would be our absolute maximum. And then for all the minimums is the absolute minimum. Okay, so whatever is the lowest of the low or the highest of the high, if you will. Okay, now that when we're talking about absolute minimums and maximums, we want to just make sure that we're looking at the correct question. Okay, so this is saying the absolute maximum value, which is the y value, is, and then that absolute maximum occurs at. All right, so if we look here, all right, at our graph, we'll see that the highest point here is right here. Okay, that's the highest point on the graph. So, and if we follow that down, we see that that occurs when x equals 3. And then the absolute maximum value would be the highest y value that it hits, which would be 2. Okay? Again, just be careful. When we're saying the maximum or minimum value, that's a y value. When we're saying where does it occur, that's an x value. Okay, so kind of think back to quadratics, like the vertex. The vertex occurred at x equals whatever, and the maximum or minimum was that y coordinate there. Now, let's look at absolute minimum. Again, we have the absolute minimum value and the absolute minimum occurring at. Now, we would look and we see, we have a minimum here, we said, and we said we have a minimum here. However, what we need to recognize is that this graph with this arrow here is continuing downward, and it's continuing downward forever all the way to infinity. So because it's continuing downward, okay, we have to assume that the y values are getting smaller and smaller and smaller and smaller, right? More negative as I continue to go down, meaning that there is no absolute minimum. Because the graph is continuing in that downward fashion, then it's never going to reach an absolute minimum. Okay? So again, if you notice on the right side of the graph, x is continuing to increase, and therefore y is continuing to decrease. Therefore, there would be no absolute minimum. All right. So again, if you want to pause the video here so that you can look at these questions and see if you can answer them, feel free, and then I will talk you through them. All right, so this wants us to find and classify each extrema. So again, the first thing I would say, if we're going to do this in like steps here, the first thing would be to look at the endpoints. Okay, that's what I would say we should do first. So in looking at this graph, I notice that we have an arrow there and an arrow there, meaning that our graph is continuing on in a downward fashion forever. Okay, so in terms of a minimum, all right, I don't have one because at no point is this graph changing from decreasing to increasing. Okay, and I also don't have an absolute minimum because this graph is continuing to go down forever. All right, now we have to look at relative maximum. So we remember relative maximums occur when the graph changes from increasing, which it's doing here, to decreasing, so there. So where it changes would be right here at x equals 1. So the relative maximum is at x equals 1. Then the absolute maximum, considering that's the only maximum on our graph there, so the absolute maximum occurs at x equals 1, and the absolute maximum value would be its corresponding y, which is 3. All right, let's look at the next example. So again, first thing we're going to check are the endpoints. Well, here we have two definitive endpoints. So we need to consider those while we're going through and answering these questions. Next thing we're going to want to look at is increasing and decreasing. So let's see, here we're increasing, and here we're increasing, and then we've got decreasing and decreasing. So again, everywhere that we see that color change, including those endpoints, we also need to consider. All right, so relative minimums. Again, it's where we're changing from decreasing to increasing. Okay, so this right there is a relative minimum where x equals -3. And then if we continue on where it's changing from decreasing to increasing, we also have one there at x equals 3. Okay, now let's look at our maximums. Now, if we're looking at this section of graph right here, okay, there is a relative maximum for that area at x equals -4 because that is an endpoint. So remember, we have to consider endpoints when looking here. All right, and if we continue on, where is it increasing and then decreasing? We also see that happen here at x equals 0. And again, if we continue on my graph here, okay, we'll also notice that this endpoint is also a relative max, so that would also be at x equals 5. Again, that is because it is an endpoint. All right, now let's look at absolute minimum and maximum. So if we look at our graph for absolute, we're looking for the lowest of the low in terms of minimums. So I see that the lowest point is when x equals -3, this point right here. And then that occurs when x equals -3 and the corresponding y is also -3. So my absolute minimum value is -3, which occurs at x equals -3. Then for absolute maximum, again, we are looking for the highest of the high, right? The greatest. So if I look, this dot right here is the highest dot there is. So that means my absolute maximum is occurring at x equals 5, and my absolute max value is 4. Okay? And then just some fun facts that are also going to be able to help you here throughout. So between two real zeros, so not imaginary, okay, so between two real zeros, there must be at least one local maximum or local minimum, okay? So if I think about what a graph looks like, if I have two zeros here, like say 1 here and here, I know somewhere between these two lines here, somewhere in the middle part, there has to be at least a local maximum or a local minimum. The second thing is that polynomials that have even degrees, so remember, even degrees, highest exponent, so think things like x to the 4th, 3x to the 6th, anything like that, must have either a global maximum or a global minimum. Okay. All right, last page. All right, so now we're saying here we have some function, okay, and we're only given this set of values. That's all we have, okay, and they want to know, do I have any guaranteed extrema? All right, so what that means is, can I be certain that somewhere on this function with these given set of points, there is an actual extrema, whether it be local or absolute? So let's first think about these points. So I'm going to number them just to make them easier. So remember inputs and outputs, right? So my first point, okay, the input was -2, output was 0. So that's my first coordinate. The second point, input was 0, output was 5. Third point, input was 4, output was 0. And the fourth point, input was 7, output was -1. So there are my points. Now, you could do this, analytically and not graph it, but I want to show you what this is going to look like on the graph. All right, so let's just, draw like a little rough sketch here. It's not beautiful. That's okay. All right, so let's look at the first point. So number 1, negative 2, 0. So we count negative 2 to the x, 0 on the y, and that gives me that point there. Next point, we have 0, 5, so 0 on the x, 5 on the y. So we have that point there. Then we have 4, 0, so count 4 on the x, 0 on the y, so we have a point there. And then our final point, we have 7, negative 1, 6, 7, negative 1, so we have a point there. Okay, we don't know anything else just from these given points about our graph. So what we need to decide is it going to have any form of extrema? Well, remember, we just said that as long between any two real zeros, and remember zeros are where they hit the x-axis, right, where y is 0. So between any two real zeros, there has to be a local minimum or local maximum. So I know that somewhere in between these two x values, there has to be some type of local minimum or maximum. So to answer this question, we would say yes, okay, and it would be on the interval. So again, somewhere between negative 2 and 4. Also, if you want to write that as an that was an inequality in interval notation, you would say it's going to happen somewhere on the interval negative 2 to 4. Okay? Now, the last piece of this puzzle is to look at the calculator practice. So what I'm going to do is I'm going to try to show you how to do this on the calculator as long as this works out. So I downloaded this calculator app here to kind of show you. So to do calculator, we look at this. The first thing you're going to do is hit the y equals, and that's where you're going to want to type in your function. So you would do 2.638. You hit the little variable button here for the x, and then underneath the clear, you'll see that little caret, which is how you get the exponent. Then make sure you hit the right arrow to make sure you're out of the exponent, and you're going to type in the rest of your function. Okay? And then you can hit graph, and it's going to bring you to your graph. Now this one says, we have a restricted domain because we're only considering values where x is less than or greater than or equal to negative 3 and less than or equal to 3. So when we're finding our answers, we want to make sure that we're only looking in that window. And again, if you hit this button up here that says window, you can change your x values to reflect that interval. So now to find a relative minimum, if you see where trace is, if you hit second trace, that brings you to the calculate menu. First thing it asks is minimum. So you're going to go down to where it says minimum, and you're going to press enter. And if you see at the top of the screen, it says left bound. So we're going to use our arrows to kind of target where I think that is. So if you can see that little baby cursor moving back and forth, okay, I'm going to say enter, that's my left bound. And then I'm going to leave my little baby cursor, and I'm going to hit enter to tell it that's my right bound. Okay, so it told me I was looking between those two lines. When I did that, if you notice down in the bottom left, it says minimum x equals 1.01293. Okay, remember, all right, that for the purpose of the AP exam, we're always going 3 decimal places. So the relative minimum here would be at x equals 1.013. Okay, again, then you're going to follow the same procedure to answer the other questions. I did post the steps on Schoology as well, okay, to help you with the calculator practice, but I did want to give you the answers to both of these so that you can do them and check them. Okay, again, we will continue to practice more with the calculator in class, but that is how you do it if you're working at home. All right, if you have any questions, I'll see you in class.